25 minutes.
Okay, check. Yeah. Thank you, Johnny, for the introduction. So yeah, as you can see from a rather long title, today I want to discuss a few strategies or give you an overview of how we can strive for superconductivity, high TC conventional superconductivity at ambient pressure. So the presentation is structured as follows. I will start by giving you a short review. I think most of people here know a lot already about hydrides, but just to set the field, I will review what we know of hydrides and what are the mechanisms that lead to high TC, and then introduce the main idea. So our main goal, that is to reduce the stabilization pressure for superconducting hydrides. And for that, I will propose two strategies. And one is the one which is very much talked about, which is chemical precompression. But there's one on which I want to focus much more, which is instead to go through doping. Then I will give you my conclusions. So let me review the mechanisms that lead to high TC. What
are you sharing
the Zoom?
Yeah. Start Zoom again.
Trial. Okay. No, I think I can start from here. It's no big deal. So of course, hydrides are conventional superconductors. What this means is the mediator of the interaction are phonons. This means that they are described by Migdal-Eliashberg theory, and so we have a very accurate and predictive theory. And all the more, this allows us to understand qualitatively the ingredients that we need to reach high TC and why hydrides are so good. So you see here on the screen the Macmillan formula as it appears in the Allendines paper of 1975. And below the Hopfield formula for the electron-phonon coupling. These are approximate formula, but they're very useful to understand why hydrides are so good in practice, and we will need a lot of these ideas later. So the first reason why we like to have a lot of hydrogen is, of course, it's the lightest element. So in this formula for TC, we see that the average phonon frequency appears as a prefactor. So we have a light element, we maximize the phonon frequency, we're happy. The other thing, the other reason why hydrogen is good is because it has no core electrons. So that means that the ion electron potential cannot be screened by core electrons. This boosts our electron phonon matrix element. Of course, this is not enough to give us a high TC superconductor. The other ingredients that we need is, again, to maximize the electron phonon coupling lambda. So we need to maximize this matrix element here. And we have learned from experience that this is boosted in directional covalent bonds. Now, usually in nature, these are found in insulators. But for a superconductor, we need to have a metal. So we also need to maximize the density of states at the Fermi level. And finally, we need, of course, a material that is thermodynamically stable because we want to be able to make it in the real world. Now, all these quantities are accessible by density functional theory and its extension. So this sets the ground for how we compute the superconducting properties and how we understand them from a fundamental point of view. Now, the way in which this has declined in all the hydrides that are known so far is that essentially we can classify all existing high TC hydrides in two classes. First class is the one of H3S, which is essentially a covalent metal. Now, what we have to think of H3S is first that its stoichiometry is not what we would expect from the chemistry we know. We would expect H2S. So we have a forbidden chemistry that also makes our system a good metal, despite the fact that sulfur and hydrogen have directional and covalent bonds. Now, in H3S, we are blessed by an optimal match of the electronegativity of sulfur and hydrogen, which is almost in the best possible spot to maximize the electron phonon matrix element. And also, we are very close in energy to singularity that boosts the density of states at the Fermi level. The result is indeed the very high TC. The other class of hydrides all belong to this sodalite-like clathrate hydrides that were discussed also this morning. Now, these are characterized by this very dense hydrogen sublattice that is wrapped around a central big metal atom. So in this case, what we see is essentially that this hydrogen sublattice is obtained as a result of a destabilization of the H2 molecule, thanks to the charge transfer from the central metal atom. And in this case, what we have is that we have covalent hydrogen-hydrogen interactions that are not as strong as in the H2 molecule, which has a closed shell and would give us an insulator. Instead, we have a sort of in-between, which allows us to have a covalent interaction with hydrogen, which give us the large matrix element, but while still retaining the metallic properties. So with this bit of introduction, I wanted to give you a summary of many possible pathways that lead to the high TC. So we start from the left, that is what we want, the high TC. And we need these three ingredients, the large omega log, the large electron phonon matrix element, and the large density of states. Now, with hydrides, the large phonon frequencies, we have them for free. We don't have to worry about them. The large electron phonon matrix element, as we saw, we can get it in sulfur hydride, for example, so with one element that is not hydrogen bonded to hydrogen, or we can get it from a hydrogen-hydrogen interaction. In the second case, we will need pressure. Now, for the density of states, we can go through multiple pathways. We can have forbidden chemistry, so we can have a composition that we would not expect to obtain at room pressure, which gives us a structure which is intrinsically metallic, but this, of course, requires pressure. We can get to metallicity by band overlap, which again requires pressure, or we can get there by doping, which does not. So in our research group, we have been focusing a lot on reducing the stabilization pressure. So we tried to set ourselves a reasonable goal, which is to achieve a TC higher than 77 Kelvin at ambient pressure. And we named this goal the superconductors that work. And the reason is that we want superconductors that can have a practical consequence in technology and energy that we so desperately need. We deemed not realistic to have at the same time also room temperature, but rather we are much more interested in going to ambient pressure. So the first way that we could go about this is to go through a pathway that has already been tested, which is to, of course, exploit the hydrogen-hydrogen interaction like in lanthanum hydrogen 10. And for that, as I said, we need pressure. Now, if we want to get rid of pressure, we can try to replace that with chemical pressure. What we mean with this not so well-defined term is that we want to weaken the hydrogen-hydrogen bonds using their chemical environment so the chemical bonding and or the local stress around the hydrogen sublattice, which will reduce the requirement for pressure. An ideal playground to do this is ternary hydrides. So we go from a structure that has a AXHY composition to one which in which we have an element A and another element B other than hydrogen. And what we gain is a much greater flexibility, because now we can play with two different atoms to really try to optimize this chemical environment. Now, so these are good candidates to optimize chemical pressure. And this is basically what led us, the way in which we understood the formation of this first hydride that was presented earlier. So we predicted the formation of this lanthanum boron hydrogen 8 structure that you see here, which becomes thermodynamically stable slightly above 110 gigapascal. But then if you compute the phonons, you see that they remain, the structure remains dynamically stable down to a few tens of gigapascal. So this has a predicted critical temperature of 126 Kelvin at 50 gigapascal. So it's quite exciting. We said this is the first ternary hydride with a high TC, and now I say at a relatively low pressure, because an experimentalist would say that this is not low. It's much lower than all the other hydrides that were discovered before. So we tried to gain some intuition on the reason why we could do better with lanthanum boron hydrogen 8 than we did in other hydrides. And the idea that we got it from comparing the crystal structure of lanthanum boron hydrogen 8 with lanthanum hydrogen 10 that you see here on the right. Now, what's interesting here is that you can see that lanthanum has exactly the same lattice. It's a face-centered cubic lattice, and it even has the same distance at equal pressure. But now, in this hydrogen cubes that stay between lanthanum atoms in lanthanum hydrogen 10, we fit boron atoms. And so we obtain a structure which is much more dense than the other. So I don't want to talk too much about this because they will be discussed extensively by my colleague Christoph Heil, but I just wanted to say that we can even further optimize these interesting crystals to further lower the stabilization pressure. Now, what I want to focus on much more is the alternative strategy. So let's say we want to get rid of pressure entirely. We don't want to reduce it. We really want to get rid of it. So we have to start from hydrides that are already thermodynamically stable at ambient pressure. But essentially, most of them, we know them to be insulators. And what we are left with this diagram is we lose a lot of options. We have to use bonds between a different element and hydrogen. And we have to use doping to make our structure metallic. Now, the idea is that doping is very difficult to do in experiments. So we really want to start from reasonable candidates. And reasonable candidates, I mean that they must have large electron phonon matrix element and they must be easy to dope. So in general, a very good playground where we think this might be possible is doping of molecular fragments. Now, as I said, this is not a completely new idea. It's more like a revamped idea because doping of covalent structure, SIMS NGB2, has been proposed for several structures like lithium boron carbon, water, or polyethylene, but has essentially always failed. It was either predicted at extremely high pressure or it was never synthesized. Now, what's quite special about molecular fragments is that they are characterized by a very narrow electronic bands, so very sharp density of states, And the intermolecular bonds are typically very strong. There is very nice work from Musa and Cohen from 2008 in which they really examine the electron-phonon coupling of different molecular fragments to hypothetically see if they could be good superconductors. Now, what's the problem in this strategy? Let me illustrate that with an example. Here on the right, I'm showing a picture of methane. So it's a tetrahedral structure with carbon in the middle. It's bound to 4 hydrogen atoms, and it has some very strong bonding sigma orbitals, which in principle have a very large electron-phonon matrix element. The problem is that methane is insulating. So if we were to apply pressure, which we don't want, but anyway, this remains insulating up to extreme pressures. And if we tried to dope it, this wouldn't work. And the reason why this wouldn't work is that we are trying to dope a molecule on a site which is very strongly bonded. We cannot do that. We are disturbing our structure too much. So doping should not involve the covalent sublattice. It should happen somewhere else. This is sort of the idea that led us to consider this family of structures that I'm showing here on the right, which are metal boron hydrides. So metal boron hydrides are synthesized using a mono, di, or trivalent metal cation, which in this structure that I'm showing here on the right is calcium, and boron hydrogen for anions. And the way this structure is formed is essentially there is a charge transfer from calcium to the boron hydrogen cation, which is isostructural and isoelectronic to methane. Now, again, these structures are insulators, but the good thing is that they are commercially available. You can buy them relatively easily. And so let's look at their electronic structure. If we look at the band structure and the density of states, as I said, they have very narrow bandwidths. So you have a very, very sharp density of states, which essentially corresponds to the methane molecular orbitals. And so it's also interesting to look at the projection of the density of states, because you can see that it's basically 50-50 boron and hydrogen, highlighting that we really have the right states at the top of the valence band. So even if we manage to dope a tiny amount of holes into this structure, we would get a very large density of states at the Fermi level in states which have a very large electron-phonon matrix element. And the metal boron hydrides are an ideal doping framework to realize this. Essentially, because of this peculiar charge transfer between the metal atom and the boron hydrogen molecule, the position of the Fermi energy essentially depends on the interstitial metal atoms. By replacing a portion of the metal atoms, we can tune almost freely the position of the Fermi energy. So in our study, what we did was replace a fraction of calcium in the alpha phase of calcium boron hydride with a tiny amount of potassium. So effectively, potassium has valence 1, calcium has valence 2. So for every calcium we replace, we inject 1 hole into the crystal. So to simulate this, and especially to calculate the superconducting TC, we resorted to the virtual crystal approximation. For the non-expert, the way in this works is that this is only reliable when it's done between atoms that are adjacent in the periodic table, but potassium and calcium are. So this essentially is one of the few cases in which this works reliably. And the idea is that instead of averaging over many supercells, we are mixing the pseudopotentials. So we take our pseudopotentials, put them in a blender. That means that we are interpolating between them and obtain a virtual atom. Now, with the virtual atom, we replace it on every calcium site. So we are effectively doing an average before doing the calculation. The advantage is that we can do continuous doping in the unit cell, and we can afford to calculate the superconducting TC, which with the current computational resources, we cannot do it for a supercell. So does it work? And the answer is yes. So you can see in this figure, I'm showing the superconducting gap against temperature, and you can see how it closes at TC. And this is for a doping of 0.03 holes per formula unit. Now, this was obtained by density functional perturbation theory and then solving the isotropic Migdal-Eliashberg equations. So at small doping, we already have a very high TC. So we can follow the trend as a function of doping. And essentially what we learn is that indeed, as the doping increases, the density of states increases rapidly. But you can see that it's already quite large at this small doping fraction. The electron phonon coupling average lambda is quite large, which ultimately leaves us with a high TC. Now, what's remarkable is that if we were to extrapolate this to lower dopings, we would still have a high TC even at smaller doping values. Now, a lot of our efforts after we did this calculation was placed into trying to be as confident as possible that the approximation that we made were reliable, because we understood that people could be skeptical about this. So we try to answer the questions: can we trust the VCA that we use? And can this system be realized in experiment? So to check the trustworthiness of the virtual crystal approximation, what I did was essentially try to think of the limitation of the VCA, which is that it cannot describe local distortion, and it cannot describe intergap states due to distortion of the cell. So we constructed a 2x2x2 supercells, and here we are talking about 352 atoms. And in each supercell, we swapped, we randomly assigned the position of calcium 10 times, and we averaged the density of states. So this was done to have a reasonable estimate of the effect that doping would have in a real case scenario on the electronic structure. And as you can see, we see that the density of states remains more or less unchanged up to doping levels of about 10%. We have no states into the superconducting gap, and we see that the Fermi energy shifts like we expect it to do when we do it with the VCA. So yes, we think that the VCA is justified. Now, can this system then actually be realized in experiment? Now, since we already constructed the supercells, we could for free obtain the formation energy with respect to doping. And so what you see here is the formation energy of the dope structure with respect to the composition into pure potassium and pure calcium boron hydride. And of course, it costs energy to put all into the system, but we see that up to dopings of about 10%, the energy cost is absolutely reasonable. We are within a range of 100 MeV per atom, which is usually accepted as a reasonable threshold. So yes, this is also likely to be realized in experiment, also considering how easy it is to get your hands on the material itself. Now, just because I have one more minute, I would like to mention another alternative strategy to doping, which does not involve hydrogen. This is a boron-carbon system, and this forms, it's interesting because it forms a sodalite-like structure very much similar to that of calcium H6 that was discussed this morning. And in this structure, the boron and carbon are covalently bonded, and they are wrapped around, again, an electropositive atom, which is donating charge to them. Now, these were experimentally synthesized with lanthanum and strontium as metal atoms. And what happens is, as long as you use a trivalent atom like lanthanum, the system is insulating. But we studied the effect of substitution of a lot of possible metal ions, and the band structure turns out to be very insensitive to these substitution. So the effect is really that the Fermi energy shifts without disturbing too much the bands. The effect is that we have, we turn the system into a metal, a hold-up metal. And if we predict the critical temperature, we get reasonable TCs. So we tried to play it a bit with all possible substitutions, and the best we could find was a 50-50 doping of rubidium and strontium, for which we predict a critical temperature of exactly 77 Kelvin, again with density functional perturbation theory and isotropic Migdal-Eliashberg. So this is, again, a promising alternative route. Of course, it's not as high as the hydride, but it's ambient pressure, which is, I think, where we ultimately want to go. So in conclusion, I think with all the massive amount of literature that we have on hydrides, this led us to understand much better how we can reach high TC in conventional superconductors. And I think reaching high TC at low pressure should be a priority goal. Now, chemical pressure is mentioned very often, and it is indeed a possible strategy, but doping molecular hydrides is a valid alternative that should be explored. So I hope I convinced you that smart doping in metal boron hydrides is extremely promising, and that we predicted a TC at 110 Kelvin degrees at ambient pressure, which, if this was realized, would be almost as good as cuprates. And that we also have alternative doping routes in boron carbon systems. So with that, I would like to thank you and all the amazing people from my research groups. And I'm finished. I'm open to any questions.